want to welcome you to the second neuroprosthesis seminar of the semester, and welcome Hugh Herr. Before I introduce Hugh, let me remind you that the next seminar will be one of our very own, John Shea. John will be talking about intramuscular electrical stimulation for post-stroke pain, and John was just became a member of the National Advisory Board of the NCMRR, and probably has a great deal of experience in outcome assessment in stroke. I think you'll find this talk really interesting, and as you will today's. Find very interesting. I'd like to introduce Hugh Herr to those of you who don't know him. Hugh has such a varied background. It's really interesting. I was telling him last night I went and I thought, I'd just sort of Google and find his CV and, kind of, I'd have all, well, I had to work harder than that, so I had to look through about 7 pages, and I gave up of all the Google references. Well, Hugh did his bachelor's degree in Millersburg University of Pennsylvania, right, in physics? Yes. And then a mechanical engineering degree, master's from MIT, and a Ph.D. in biophysics. So you already get the idea that Hugh has a lot of dimensions in how he thinks. He is truly an engineer, a scientist, an inventor, an innovator, an entrepreneur, an adventurer, a climber. He has founded a company named iWalk. Maybe you'll mention that, some of the things today, and how the technology is coming out in order to bring the technologies that he has imagined and invented and tested and bring them all the way through the cycle. So this is exactly the kind of person who wants to see the realization of the ideas and the creativity that he has reach people. And I think many of us exactly resonate with that, and we're really excited to hear about that. Hugh has also won the Popular Mechanics Breakthrough Award, 2005, the Heinz Award, and has had a book written about him. And when I was sort of leafing through that, that's what I was looking for Hugh. So I bought it last night, so I can't give you more facts about yourself, but let me...
Your mission is to embarrass me.
Let's all welcome Hugh Herr.
Thank you for that warm welcome. So I direct the biomechatronics group. It's physically located at the Media Lab at MIT. I have a dual appointment between architecture and a program called Health Sciences and Technology that spans MIT and Harvard. So my research group, we wish to advance the science of biomechanics and movement control and apply that to the development of wearable devices. We focus on legs primarily, so prostheses, orthoses, exoskeletons. I'm interested in this field because of the profound need out there. This U.S. soldier here is hit by a blast near Baghdad, and as you can see, he's missing 3 limbs, an arm transradially and 2 legs transfemorally. This is what current technology can provide, at least commercially available current technology. So it's our mission to advance systems to improve the quality of life of this gentleman, as well as people like him worldwide that suffer from some type of limb pathology. Our first adventure into prosthetics was to develop a variable damper knee. The knee uses magnetorheological fluid. Many of you may have played with this fluid in your research programs, but in the shear mode, if you put the fluid between 2 plates and you apply magnetic field perpendicular to plates, then the force necessary to shear the plates is increased because you have to break the magnetic bonds. So if you look at a coronal section of the artificial knee, you'll see very fine lines here. What you're seeing there is a clutch pack architecture. So as the knee is flexed and extended, there's thin discs moving relative to one another. And in between the discs is MR fluid, is a thin film. The gap size is very small, 17 microns. So we have a magnetic circuit here, a return path with an electromagnet that we can use to vary the magnetic field through the entire stack. By doing so, we get a very large dynamic range from 0.3 Newton meters the whole way up to about 60 Newton meters. In terms of control, we pursued a controller that's adaptive. So the goal is that the knee is attached to the residual limb via a socket, and the algorithm adapts the damping levels throughout the gait cycle automatically, allowing the patient to walk at different speeds and across different terrains. Crudely, the knee is able to detect different terrains. I say crudely because the knee knows it's going down something here, but it can't tell the difference between steps and a slope, which is a problem. Nonetheless, if you attach a very sophisticated biological system, the human, on top of this, the device does wonders. So this gentleman decided to walk on top of a wall. So my goal today is to convince you that this is a really bad design. That's my goal today. We have a new knee design, and I'll explain further in just a moment. In the area of orthoses, we've developed a powered ankle-foot orthosis. Here we have a motor system attached posteriorly. Crudely, this is a muscle tendon-like. There's series compliance. We sense how much energy is stored in the series springs, and essentially we do a position control on the series spring, and by doing so, we can do a force control in the world. So throughout the gait cycle, as the drop foot patient walks, we can have the orthotic joint behave like a damper, a spring damper, torque source, whatever we want. Our primary mission is to provide an assistance to people that have suffered a stroke. This gentleman has, as you can see, the classic drop foot pathology, sitting on the ground with his forefoot instead of his heel. So it turns out if you build a robot, wrap it around the patient, the robot pushes on the patient. With the right control and the right electromechanics, you can improve symmetry and also the ability to walk at high speeds. Many people view this cord as a pipe dream. It is not. This device only consumes less than 10 watts electrical. So we're now packaging this, so with a normal pant leg, you won't be able to tell that a person's wearing it. We tested this on just a few patients, but they all, in their testimonies, said that it improved their locomotion a great deal. That was surprising because the device has mass, of course, but no one complained about the weight of the device. More ambitiously, we're building robotic legs that span the entire human leg. The goal is to make walking and running easier, whether you're disabled or not. This person is not disabled. He's wearing a backpack and that weighs about 100 pounds. And on average, 80% of that load is transmitted through the robotic legs, not the human leg. The architecture of this mechanism, most of the things we develop is motivated by biological models, morphological models of the leg and neuromechanical models, which I'll get into in a moment. Because of that, this robot is very, very low power. So when he's walking there with 80% load transmission, the device only requires 2 watts electrical. Okay. We're also interested in augmenting hopping and running. So this looks incredibly silly, I know, but as you know, when animals and humans run, the entire leg behaves like a spring, and it's even a linear spring. So the idea here is, can you build an exoskeleton that provides that that spring compliance in parallel to the human. So this is, imagine that you have a trampoline attached to you in parallel. As soon as your foot hits, you can relax your leg because the exoskeleton is offering that compliance. So using measures of metabolism, how much oxygen is used by the subject and how much carbon dioxide is expelled, we've shown by tuning the compliance of the parallel spring, we can get reductions up to 30% in metabolic cost. We're now attempting to do the engineering for running. It's a bit trickier to do running, but we anticipate these very large reductions in metabolic cost to run with the exoskeleton. The dream here is that we can deeply affect metabolic cost, but not affect stability. So in the future, there'll be these exoskeletons, these fancy pants, where you can put on run, not breathe hard, but still have the ability to go up and down steps over rough terrain. So now I'm going to transition, sort of some of the projects we've done in the past. I'm going to transition to challenges that researchers in this field face. So we need prosthetic and orthotic leg systems that are economical for cyclic, steady state moving patterns such as walking. So what do I mean by that? So I showed you this Rio knee that's now a commercial product earlier. So this system that you see here has a passive elastic ankle foot. This gentleman's wearing a flex foot prosthesis, and the knee is a variable damper. So because of the mechanics of those devices, they're not capable of capturing the mechanics of the human knee and ankle joint. We believe because of that, this gentleman is using more food energy than a person would with intact limbs. So what I mean by economical is both the robot itself has to be economical, has to require very little energy from a power supply. And when you attach it to the human's energy has to be low. That's the research goal. So now this system only consumes 1 watt electrical, but it's terribly costly for the human because of the pathological joint mechanics offered by the prosthesis. So what is your ankle? What does it do, assuming you have biological ankles? So here's plotted mechanical power normalized by body mass versus percent cycle. By convention, 0% cycles heel strike, 100% is heel strike of the same leg. There's 4 curves. This is slow walking, moderate, and fast walking. These data were, these estimates are from an inverse dynamics calculation. So the take-home story is the faster you walk, the greater are these power spikes at terminal stance. And in fact, the faster you go, the greater is the net work done by the ankle. So even at a moderate walking speed at 1.3 meters per second, the ankle's on average doing about 10 joules mechanical net work. So conventional prostheses that are built from passive springs, of course, are not able to capture these energetics. This is very important. Biomechanists now believe that these high powers in the trailing leg are critical because that high powers get off right before this leading leg hits the ground. So those high ankle powers, in fact, reduce the impact losses at heel strike. It's not surprising to us that 70% of amputees have back problems. They're just hitting hard with each step. Knees, here's again mechanical power versus gait cycle. Yes, you have negative power regions at the human knee, but you also have very large, substantial positive power regions, even for steady state level ground ambulation. So something like the Rio knee and the C leg and all these variable dampers on the market today obviously cannot capture these positive power components. So that's another reason why we believe you have high metabolism, low walking speeds, stability problems with walking amputees. So we asked the question, so if you look at the history of design in leg prostheses, the designers were really smart. They used quasi-passive devices, such as a variable damper, and passive devices, such as springs. And the reason is you can build those devices at low mass, If you need a power supply, the power supply is very, very small. You can build those devices robustly, and they're quiet. You don't hear them as the amputee walks by. So it's exceedingly difficult to just throw motors everywhere. Okay? If you're not careful, you end up with a device that doesn't work, that no one wants to use. So we asked this question: would it be possible to build a device where you can capture the mechanics at the knee and ankle, where you're just varying impedance for the most part, and doing just a little positive work with a single actuator? So this is an abstracted musculoskeletal representation of the leg, wherein we only have 3 muscles. We have 2 monoarticular flexor extensors at the hip of the model, and one unidirectional actuator or muscle representing the soleus. All the other muscle tendon units are modeled as series elastic clutches. So you can think of this as an isometric muscle control where the energy flow goes through the tendon, or the combination of the tendon plus the muscle leads to a series elastic clutch operation. So we performed an optimization where we varied the stiffnesses, the clutch times, and we asked the question, can we track what the knee does in level ground walking? That's an interesting question, because note that all the elements that span the knee in this model, they're all quasi-passive, okay? They're just springs and clutches. So the question is there a set of springs and a set of clutch times where we can capture the torque and power profile at the knee? The answer is yes. So even though there's positive and negative work cycles at the knee, you can do that largely elastically. So here's the model result and the mean plus or minus standard deviation of what we believe the biological knee is doing from inverse dynamics. So again, because all the elements were quasi-passive spring clutch elements that span the knee, and because the net work at the knee is typically negative, when you integrate power versus time in walking, you particularly get a negative number. What has to happen is the biarticular elements of the model has to transfer energy either from the knee to the ankle or from the knee to the hip. What we found in the model is there's very little negligible energy transferred from the knee to the ankle, but there's substantial energy transferred from the knee to the hip. So not only can you capture knee mechanics using these elastic quasi-passive elements, but you can transfer mechanical energy to the hip to reduce the actuator work at the hip. So this model, you can see per leg only requires 24 joules of actual concentric work from the actuators in the model. Very low energy. This is a plot of whole body mechanical energies. Typically this has been studied, but since no one can estimate the amount of elastic energy storage in tendon and muscle, typically you see these plots only for potential energy and kinetic energy. So here's all 3 components. The dark line is the total elastic energy storage in the body as estimated from the model. And this curve is the potential plus the kinetic energy of the body in walking. And then this thick line here is the total mechanical energy. So you see, since this underactuated leg model can capture the mechanics at the ankle, knee, and hip, it's not surprising that this elastic energy storage is out of phase of the other mechanical energy. When you add them together, you get a fairly horizontal line in time. So what we believe is, A, elastic energy storage in walking is critically important. Okay? Not only in running, it's also critically important in walking. The tendons are doing a great deal. And if we're going to build prostheses and orthoses and exoskeletons and humanoid robots that walk like us, we really need to put springs all over the leg. Okay? In this model, the cost of transport, or the muscle work, normalized by the weight of the person multiplied by the distance traveled, that's believed to be around 0.05, between 0.05 and 0.06 for humans. And when we run this model across 9 human walkers, we get a similar value. So this model seems to capture the amount of energetics or positive work required for walking. We're also exploring how such a model might be controlled in a forward dynamics sense. Years ago, Hartmut Geyer, a researcher in Germany, put forth this very simple model of human hopping. In this model, the whole mass of the body is a point mass on top of the massless leg, and there's a single muscle, a knee extensor muscle. And he asked what reflex would produce stable hopping. And he found that a positive force feedback was very effective. So in this simple feedback, you measure the force borne by the muscle that's fed back, and then you modulate the activation of the muscle. So what he found is that this simple feedback stabilizes hopping. So the model, in steady state, the leg behaves like a spring. And if you apply a disturbance, if the disturbance takes energy out, the muscle, the model automatically injects energy in until the model comes up to the same mechanical energy level. If the disturbance injects energy in, then the muscle automatically dissipates energy to bring the mechanical energy down to where it was prior to the disturbance. So we asked, could such a reflex be effective for a human-like walking model? So we put in hill-type muscle models, tendon models in this representation. For the muscles that span the knee and the ankle, muscle extensors, we used the positive force feedback. For the agonist muscles, we used negative force feedback. For the hip musculature, there's a simple feedback to keep the pitch of the upper body upright. So what I want to note is you see the ground is continually changing. The model, of course, has no knowledge of that changing ground surface, has no vision or so what you see is here's a fairly interesting robustness to disturbances. So this model is purely reflex-based. There's no oscillators in the model whatsoever. What's interesting is that, I'll say it again, all the muscles that span the knee and ankle, they're not feeding back any position information. It's only force information. That's a paradigm shift in the robotics world. As many of you know, humanoid robots typically use a ZMP control, where the controller has a desired center of pressure or ZMP trajectory, basically where the researchers want the feet of the robot to land. And then they do the mathematics to what the joint trajectory should be for the robot to assume that ZMP trajectory, and then they do a high gain positional trajectory control. The problem with that approach is you never, if a banana peel is thrown in front of the robot, no one really knows how to compute new trajectories, new appropriate trajectories. So this suggests maybe we don't work that way. Maybe force feedback is even more important than position feedback. So I'm going to transition now from the modeling work to the device work. So in recent history, we've focused on robotic knee-ankle systems and knee systems. This is, as you can see, a foot-ankle system. So I want you to note the facial expression of this gentleman. At the time of this video, he had worn this device for 30 minutes. Okay, and he's been an amputee for 5 years or so, always used a prosthesis, the best prosthesis money can buy, carbon composite, energy return prosthesis. So it shocked us that this gentleman liked this device. And the reason is that the robot itself weighs 6.5 pounds, and this backpack that has all the motor drivers, electronics, and battery weighs 13 pounds. But this guy is happy. He actually liked this. And the reason is, if you apply the rate control at the ankle, the amputee won't feel all that weight. So by actively power planar flexing, the device can to some degree lift itself. And also those high powers, as I mentioned previously, we can reduce impacts of the leading leg. So to quantify his smile, we did a pilot study across 3 people. We've expanded this to an additional four subjects. But what we get is, for metabolic cost of transport, is fairly large reductions between a conventional prosthesis and the powered device. Again, the conventional here was the high-tech flex feet and whatnot, high energy return feet. So for unilateral transtibials, healthy unilateral transtibials, the difference between a normal metabolism with intact limbs and their metabolism can be as low as 10% using flex feet. So this suggests that we may be actually normalizing metabolism with this robot. Very exciting. In this pilot study, for 2 of the subjects, their self-selected walking speed didn't change. One of the subjects, it increased. This particular subject, his self-selected speed was 1.45 meters per second, very fast walker. With power and control, he was boosted up to 1.67. But note, even at that higher speed, his metabolic cost of transport was lower than at the slower speed. So we have an opportunity to shift the cost of transport curve to the right towards higher speeds and also shift it down. Very interesting, in these trials, we had the patient control the device. The patient told us what stiffness it should be, how much power should be delivered, the timing of that power. We would just say, what do you want? Do you want to be stiffer, softer? And these are a bunch of young guys, so they naturally asked for more and more and more and more power. To the point where the robot was being saturated, and this limp emerged, wherein the patient was putting more load on the artificial side than their biological side. So I call it human laziness. If you have a prosthesis that's so powerful, and the patient has, control the knobs, they'll just power themselves so much that a limp emerges, and it's this weird asymmetry, and it's actually the lowest metabolic cost for that human-machine system. A bit about the design. Foot-ankle system, there's a reason it hasn't been done in the past. It's a really hard problem. So you need a weight that's equal or less than the human weight, mid-tibia down. The height has to be modest because you have different amputation levels. A classic amputation is 8 inches distal to the patellar ligament. So if your device is too high, then you can't match heights on both sides for a unilateral patient. Peak power, the ankle, human ankle often does several hundred watts mechanical. Peak torque is 140 newton meters in that range. Has to be very fast, high torque bandwidth. Shock tolerance, because it's the distal joint, you have blam, blam with every heel strike. We need to do force control, has to be low energy consumption. With a single small battery, the patient has to go throughout the entire day. It has to be safe, of course, and quiet. This quietness is, I stress often, is very, very difficult. We want a device where the amputee can be wearing this, come into this social situation, late for a lecture, and not have everyone look to the right because they hear the grinding of the gears and motors. Okay. So that what the device, the target behavior of the device for normal walking is described here. Here's ankle torque versus ankle angle. 1 is heel strike, 2 is forefoot collision, 2 to 3 is loading or controlled dorsiflexion, and 3 to 4 is power plantar flexion. 4 to 1 is the swing phase. So note again, at normal walking speed, you have loop area. So this area in here is roughly 10 to 15 joules mechanical. So how do we do that? The key here is architecture. So how the ankle is designed is there's a motor and transmission in series with a spring, and the series spring is a tune stiffness. And that entire series elastic actuator is in parallel to a unidirectional spring. What I mean by unidirectional is when the ankle is 90 degrees, the spring is engaged. And the spring stores energy as the ankle goes into dorsiflexion. But in plantar flexion, the spring is not there. Okay, so what that does is you can dramatically lower the forces borne by the actuator when the forces are the highest here at peak dorsiflexion. So basically, we tune that parallel stiffness to be equal to the slope from 1 to 4. This is the desired trajectory, torque trajectory, so that the motor only has to do some of the work, or the net work. The work that it absolutely has to do. The rest of the work is done by passive compliance. When you do this, you actually get you increase force bandwidth of the actuator, and I'm convinced only through a parallel elasticity can you get several hundred watts mechanical with a package that's small enough and efficient enough for a prosthesis. So here's an optimization plotted vertically as the series stiffness, and on top here is the parallel stiffness, and versus transmission ratio. So it doesn't take much convincing to know that the optimal parallel spring stiffness is 100%. So when a person walks slowly and you take the slope of the torque angle curve, that's the stiffness we use for the parallel spring to give us the lowest energy, which is shown here in color. In terms of series compliance, you want to be really, really soft. You want to have a catapult type control. So as the ankle's dorsiflexing, you want the motor to wind up the series spring long before you actually enter into paraplanar flexion. So then you get high motor speeds and high motor efficiencies. So with this device, the best we've done is about 25 watts electrical for about a 15 to 20 joule network mechanical, which is sufficient to have a battery that's about 0.25 kilograms. So we're now exploring control methodologies for not only level ground, but also for stairs. So here what we do is we model the missing limb in a musculoskeletal representation. And the robot measures its state, its positions and velocities. We input that into the model, and the model tells us what torque the joint should act at. And then we have a force control on the robot that tracks those torques. So the goal here is that if your model is coherent, the prosthesis will behave as if it has muscles and tendons and reflexes and exhibit that adaptiveness as the terrain changes subtly that I showed you earlier with the forward dynamics model. Recent history, we've gotten rid of the backpack, so all the electronics are in this back. There's a small power supply, a battery underneath the pant leg. This is still too large. This will fit into a size 13 male shoe, but certainly not a size 5 woman's shoe. So there's a very difficult scaling problem. This one's old, our newest model. It does in fact scale across shoe size. And the current weight of the robot, including power supply, is 4 pounds. So we're much better than the 6.5 pounds where we got the metabolic reduction. So I anticipate when the engineering is done, we'll be able to augment amputee metabolism. That is to say, an amputee will be able to walk with lower food energy than you can walk. Why? Because the robot has its own power supply. This is to convince you that we are in fact doing net work. So these are data experimental from the powered prosthesis. So here's I think it's about 20 joules mechanical the robot is doing. Okay, so I showed you in the model that there's of course a gastrocnemius, which is biarticular spanning the knee and ankle. I'm an amputee, so I'm transtibial, so obviously in a transtibial amputation, I'm no longer wired up mechanically properly. I don't have a working gastroc. I believe that's a very big problem. So in a new project, we're building an artificial gastroc. So first of all, we changed the socket to be integral with a knee brace. We have this mechanism that we can control in the following way. So you have heel strike, And then you have early stance knee flexion. During early stance knee flexion, these clutches are open, so these springs are not engaged. When the knee extends, the amputee has to stretch these tendon-like springs. And then at terminal stance, that spring energy helps the amputee lift the leg off the ground. So you often see in amputees a hyper hip flexion. And amputees do that to try to get the mass of the prosthesis off the damn ground, because they, in my opinion, they lack a gastroc. So with this device, there's actually stored energy at the knee. And when you lift the leg off the ground, the knee pops up and lifts that distal mass for the amputee. So you don't have to have excessive hip flexion. So here I'm walking with 2 powered ankles and 2 gastroc-like knee mechanisms. What's very interesting here is I walk for a while, and then when my students turn off the knee, bringing me back to the conventional socket, before they turn it off, I tell them that it's not working. I don't feel this knee spring. When they turn it off, I practically fall over. And my knee, I can feel my knee tighten and the muscles about my knee co-contracting. I feel less stable. My knee feels wobbly. As soon as you turn that gastroc-like force on, it feels natural. It's very interesting. Knee, I promised you I'd make fun of the Rio knee, so here we go. So the Rio knee is a variable damper. It just throws away energy. So this valuable human energy, it just converts that energy into heat. You can't get that heat back. So I showed you this under-actuated model. You can just track what the knee does with elastic energy storage and not throw out energy as heat. So motivated by this leg model, we have a knee design that has 2 motors and 2 tendon-like springs. But notice they're unidirectional series elastic actuators. They're not attached to the output. So the motors can spin and move these springs out of the way, and you can rotate the knee without spinning any transmission or motor. So there we can exploit passive dynamics, the exchange between potential and kinetic energy. And then when they're not engaged, the motor can position the spring to a desired spring engagement point at 0 load, and then just wait for the output. So position, lock the motor shaft, wait. Okay? And by doing that, you can largely track what the knee does at exceedingly low power and low noise. So here's the actual schematic and the knee itself. So here are data from a transfemoral amputee. So here's the motor agonist and antagonist engaging. You see this behavior as here's one spring storing energy during early stance knee flexion. As it starts to release its energy, the second spring engages. So you need independence between agonist and antagonist actuators. But at 8 watts electrical, we can largely track what the human knee does. Here's a video. So because this is a monarticular design, remember the key of those biarticulars? Since this device doesn't have that, yes, we can track what the knee does at low power, but we're not able to shuffle energy to the hip to lower the work of the hip musculature, okay, which is a problem. So I still anticipate that the amputee will have a higher metabolism with this device, but it'll be lower, I believe, when it currently is. Again, we tune the series compliance, and there's values of series springs where the motors are doing actually no work at all, no positive work at all. So what this model is so during the swing phase, the motor is actively back-driven. We do regen, put half of that energy into a battery, and then that will pay for the energy needed during stance from the motors to simply lock and have the springs do the work. So what we're iterating towards is a knee that requires a battery, but if you only walk on level ground surfaces, you need not charge that battery, and you can track what the human knee does. So we're now beginning to attach the knee to the ankle. No clinical data yet, but we're quickly racing towards a fully robotic leg. A little bit about stability. Again, because of these mechanics, amputees have an impaired stability. It's a major clinical problem. We all know that humans, we have extraordinary balance capability. So I love this video. So what this gentleman's doing to stay on this tightrope is actually modulating his own angular momentum, and that exerts a force on the center mass that keeps his center mass over the foot or over the wire. So that's something that current humanoid robots don't do well. So there's two key ways that humans balance. So I have two toy models here to explain. So this first toy model, all the mass of the body is a point mass at the top of a massless leg and foot. So imagine there's a motor here, and this is a crude model of standing on one foot. So this model can balance if this center mass position is within the foot envelope. When it's outside the foot envelope and you start with zero momentum, there's nothing this model can do to stay upright. It just falls over. And the reason is the horizontal force that it can exert is proportional to the difference between the center mass position and the ZMP position, or where the ground reaction force acts. So if the center mass position is out here, the restoring force is not restoring at all. It's pushing the mass away from the foot, and the model falls. That changes when you relax the point mass representation constraint. If you now have a distributed mass where you can spin this and generate angular momentum, you have two terms now. You have a second term that has to do with the moment about the center mass of the body. And this can be manipulated and actually affect the force. So with this model, the center mass can be outside the foot and it can still stabilize. So I can demonstrate, try to do it here. So if I'm leaning against the wall like this, my center mass is outside my foot, and the only reason I'm upright here is because of the wall. If you take the wall away from me, what do? I do that, right? If I didn't have that mechanism, I would just fall right over. So we've developed humanoid models now that exploit both of these balancing regimes. So you can apply a disturbance. Even though the foot positions are constrained, it can use its own mass to increase its domain of stability. Neural interface, I'm very interested in this area, and I wish to team with others working in the neural technology space. Obviously, we need a peripheral neural interface for someone like me, an amputee. Two key strategies is to develop implants to go into muscles, residual limb muscles, to measure the electromyographic information, as well as techniques to communicate directly with the nerve. So I've been collaborating with others, and one reason for my trip here is I hope to begin collaborations with many of you in this area. Just a small note, we asked the question, if you had just a small amount of neural information, what would you do with it in legs? In the context of robotic limbs that have lots of sensors, lots of adaptiveness, what would you do with that information? So our answer is that, well, let's give the amputee a remote control. When they see steps with their eyes, let's allow the amputee, by flexing their muscles, to simply switch between repetitive patterns outputted by the prosthesis itself. So here, using wire electrodes, I'm in control of the position of the ankle when it's off the ground. When it's on the ground, the intrinsic controller is varying its impedance and doing all that control work. When I get to the bottom, I can switch back to the level ground algorithm. So my point here is, with an absurdly simple algorithm and just a small amount of neural information, we can make a tremendous clinical impact. So it's very exciting. I'll finish up there. I'm probably running late. My lab runs between 15, 20 people, depending on funding levels. I'm very blessed to work with so many talented people. We have high school students the whole way up to people walking around with gray hair. So how I set up my lab is half of my lab are staff and half are students. And the staff people are very, very experienced designers. And I find that's very good for education, because I can't be there every moment of the day. And it's also critical for delivering these very complicated electromechanical systems. I'm very grateful to our sponsors, the VA and TATRIC, the Army. So the key idea here is, this is really good news. I hope you can take that away from my lecture. So it's been the opinion of some people in the field is that we can't make progress with these wearable robotic systems because we need a magic battery. We need really high power density and energy density. We don't have it yet. Or we need an actuator that behaves like muscle. What I hope to convince you today is no, what we need is a deeper understanding of how humans work. You know, all the devices I showed you use regular motors, regular springs. It's the architecture. It's how to use tendon-like compliance in the context of current motorized systems. The control, reflex-based control that makes the difference. Just a note, I was the expert witness along with my colleague Roger Crum in the Oscar Pistorius case. Many of you probably have heard of Oscar. He's a South African runner born without fibulas. He's an exceedingly talented athlete, and he actually entered into able-body races. His competitors were running with intact limbs in the 400-meter. He often beats people with intact limbs, and he was banned by the IAAF because they claimed he was cheating because he has artificial legs. And we testified in the appeal that the scientific evidence did not yet support that conclusion. So if you have questions about this, I know this topic very well. I'll finish up there. Thank you. I take a question or comment? Yes.
I'm interested about the positive force feedback mechanism. Is that really like for propulsion? You know, what prevents that force from going to, you know, the saturation point of the actuators?
The swing phase. So you only apply it during controlled dorsiflexion and paraplanar flexion. As soon as the foot gets off the ground, we go to a position control. That's why it's not divergent.
So it switches.
So it has tremendous properties. So when I walk slowly, my ankle takes energy out. When I walk a little faster, it's spring-like. When I walk faster than that, it starts doing network. Those videos I didn't mention, the ankle knows nothing about my walking speed. It doesn't care. It doesn't need to know. Anybody here ever use the Segway? It's crudely like the Segway. Segway, when you want to go faster, what do? You lean. So in the ankle, when you want to go faster, you just push on it more. So when you go downhill, it takes energy out for you. The loop is clockwise. When you go uphill, it's counterclockwise.
Let me ask an engineering question about your force controllers. To what extent is your, I guess, progress limited by your inability to achieve an exact force, or is it robust to, I mean, your force control is not perfect, or is it close enough? Is the technology?
Oh, okay. Yeah, it's close enough. Okay. Yeah, it's we don't have a fundamental problem there, thankfully. Thank you.
Hugh, you haven't said anything about sensation.
Right.
And I'm wondering if, you know, in your personal experience or in that of your, you know, of your people that are participating in your program, if they remark in any way about, you know, the lack of perception being a performance barrier. You know, I don't know where my feet are. I'm slipping. You know, that sort of thing.
Yeah, so with the systems we're developing, my hope is we'll solve the walking speed problems. Amputees typically walk more slowly than people with intact limbs. I think we'll solve the metabolism problem. What we won't solve is the balance problem. And I think that's going to require a sophisticated neural interface and actually have feedback of tactile sensation between the foot and the ground. So, you know, humanoid robots, they do the ZMP control, which was the zero moment control that I mentioned, where the ankle is modulated and you change where the center pressure is beneath the foot. That's a very important balancing strategy. So to do that, we need to be measuring motor intent, sending it out to an ankle that has 2 degrees of freedom that are actuator, not 1 that I showed you here today. We then need a foot that's measuring the pressure field, the force field, describing the foot-ground interaction. That has to be fed back to the human. I'm skeptical that simply a vibrotactile display will work. So I'm hopeful with your work and many of your colleagues' work here to try to get that afferent feedback into the nervous system. It's critical for balance. Any other questions or comments? Yes?
How loud are the prosthetics that you showed?
Another value of the positive force feedback, and I didn't anticipate this, is it's a really low noise. And the reason is as soon as the torque on the ankle is lowered, the current in the motors plummet. So you can avoid really high speed regions. Right now the ankle is if I'm walking and there's any type of ambient noise, you won't be able to hear the ankles. If it's absolutely quiet, you'll be able to hear them. So right now they have an acceptable noise level comparable to upper extremity systems. But I think we can do even better. We have a world-class design team putting together the bearings and the transmission. And they're doing a number of things for noise attenuation, such as drilling out the screw and putting noise attenuating materials in the core of the screw. So we're going to go even quieter. Yes.
I'm surprised when I looked at that you're looking at a neural interface for the feedback, and following sort of along the lines that you were working. I'm surprised you didn't use an accelerometer in there.
We do.
In your design.
We do.
Oh, okay. I didn't see it. Did I miss it, or?
I neglected to mention it. There's many things that I haven't mentioned. I rely on you for your questions. We put every sensor known to man and woman on the device because in the absence of a neural interface, we need to know as much as we can. So we have a 6 degree of freedom IMU. So 3 accelerometers, 3 rates. And that's a very powerful tool because what we do is, here's one foothold. We can start to integrate, and as the foot comes off the ground, we know this position vector. We know the position of the foot relative to the last foothold. So at the moment when the foot hits the ground again, if the slope hasn't changed between footholds, we know the ground inclination within a few degrees. So only if the ground does this between footholds do we have an issue. So yeah, the IMU is a very powerful tool. So what I'm intrigued with is if you had a fantastic neural implant and a fantastic intrinsic robotic sensory system and control system, how do you blend those, right? So that example I gave, well, you'd probably use the neural information to modulate about that nominal value that's given to you by the IMU. So the amputee will know that the intrinsic controller will get it right if the ground is not changing continuously, but it'll fail when the ground is changing. So they'll then know to modulate their neural commands in that situation.
I also noticed that in one of your movies, the subject was walking down into a trench, across a trench, and then they stopped. And I didn't see the person going up the trench.
It was a person or a model?
Person. Up the other side of the trench. It looked as if there was...
Was it a prosthesis or an orthosis?
Prosthesis.
Okay.
Yeah, you said they were going, they didn't know whether they were going.
Oh, the knee. The knee.
What do they encounter when they're... Is this a problem, or this was just something I picked out spuriously?
Yes, it's a problem. The challenge of building prostheses that are variable terrain vehicles is largely unaddressed. There's attempts that have been made, but I mean, when assuming you have biological ankles, when you go from level ground to stair descent, stair ascent, your ankle fundamentally changes in its mechanics. Okay, and you have to detect that transition right at the right moment. Because if a device thinks it's on steps and the patient's actually on level ground, they will fall. Because the stair descent algorithm, you plantar flex the toe, you hit toe first. So if the device thinks it's on level ground and does that, the patient will probably fall. So we have to detect these transitions very, very accurately, and we have to have robotic systems that are actually capable of human-like mechanics within each pattern.
Look at the interface between the robotic device and the user. Is a less than optimal fitting socket able to be modeled and accounted for, or is the most rigid possible attachment to the body, necessary for these to work?
Not necessary, but ideal. So for these powered systems, I would recommend the very intimate suction sockets, and long-term, hopefully, osseo implants. But certainly we design that the systems will offer benefit for any socket, but it's even better the more intimate the interface becomes.
So I think the series elastic element control, power control for the prosthetics is really cool. I was just interested to hear your opinion. So we deal with people who have limbs intact but might be paralyzed.
Yep.
How applicable do you think it would be in an orthosis or something like that for these kind of patients, where the limbs and muscles are still there?
I think it would be beneficial. We're developing. I mentioned we're finishing the design for the powered ankle foot orthosis, and we're also launching an effort to build a robotic knee brace. So that the patient will, with their cell phone, will be able to modulate their impedances, or their practitioner will. The value of robotics is, with the current, where we are technologically in the world, we can do a very nuanced control. In the coming decade, we'll have a knee brace that knows you're on steps, can take out energy, and make it easier for the biological knee. It can behave like a spring when the patient starts to run, can power the patient when they go up a hill. So another thing I'm intrigued with, which I'd like to talk to you folks today about, is how do we integrate FES systems with wearable robotic systems in a coherent way? Maybe the robotic system can be used as training wheels to the neural system. That in the beginning, there's a hybrid until the neural system is fully identified, the control system. And then maybe the external actuators are no longer needed for the device. Yes.
I'm interested in the challenges that you're facing now as you move this to industry. Mm-hmm. And I can imagine that that you're having a lot of redesign going on to make this thing more producible and all that. And what's your vision about well, let me just keep it wide open for a second. Really, these challenges that you face as you take, sort of address what might be, sort of classically called a small market, right? And moving a new technology when there's already, some people in the space, and how are you envisioning that within, to the extent that you can within the company?
What I'd like to see is the folks doing the inventing start the companies. I think it's there's a lot of skeletons on the pathway of researchers, inventors approaching companies and trying to sell their inventions or get their inventions licensed. Because companies have their own trajectory, and there's some mentality of invented here, and they don't believe in the invention as much as the inventor does. So 9 times out of 10, in that scenario, the project fails. So what I'd like to see is researchers team with business sophistication and smart money, and actually build companies. I think that's the winning model. And I think the prosthetic and orthotic domains, the domains in which we operate, are very susceptible to very elite startups. So the big boys in the industry in this area, I think won't know what hit them if that happens in the future. Because if you team business smarts and technology scientific smarts with venture capital money or SBR money or both, you can get there much faster than these established companies that are a little slow and cumbersome. So I'd like to see the whole industry flip upside down, actually. Yes?
When the system is turned off, is it as stable as like another conventional prosthesis?
Great question.
And if it isn't, like, do you have an idea for a fail-safe?
So a design constraint is that it has to have a fault that's friendly. So I'm very excited about this. For the ankle, for any fault, low voltage, battery dead, sensor failure, motor too hot, the system closes the motor leads. Okay? So it behaves like, the motor system behaves like a hydraulic damper. But there's series compliance, there's parallel compliance. So even when the motor leads, when the amputee walks quickly, it feels like a flex foot. When they walk slowly, it actually adapts to different surfaces because the ankle can modulate. So my dream is that even when the battery goes dead, it's still a better foot than any foot available. I don't know if we'll succeed, but I assure you it's exceedingly safe when things go awry.
Now that you're using muscle actuators and it seems like you don't really need those passive springs anymore in the foot. Is there even a need, or do people look at replicating the soft tissue properties of the foot? Is that?
Oh, the foot itself.
The foot itself?
Yeah, I didn't mention that. So I mentioned parallel elasticity, series elasticity. In addition to those elements, what's critically important is elasticity that represents the compliance of the heel pad and the longitudinal arch of the foot. You have to have that just to protect the motor system. So yeah, we attached to the robot is simply a low profile carbon fiber foot. We tried a design trajectory that didn't include that, and we got into trouble. So I know that's an important element. Thank you.